Okay. So let's take a look at this here. So explore here, the thing that I'm going to have you guys kind of try and do some on your own. It says investigating ways of solving simple quadratic equations. Again, we already have looked at solving some more complicated quadratic equations, but now we're going to look at solving them using square roots and things, okay? So there are many ways to solve a quadratic equation. For example, what we saw up here. Here, we're going to use three methods to solve this basic equation, x squared equals 16. We're going to graph, then factor, and then take square roots. Okay? So, let's solve this by graphing, right? So, we're going to solve this by graphing, and so we're going to first treat each side of the equation as a function. So that means we're going to graph x squared as one thing, and then we're going to graph the 16 as another thing, and then we're going to look for where the two things, the two graphs, will intersect, right? All right, so let's graph this. So how can we go about, well, let's graph the 16 first. How do you go about graphing 16? What's that look like? What is it? Okay, we're going to put it on the y-axis. So there's 16 on the y-axis, and then what else are we going to graph besides just that little point? The line, yeah, a horizontal line through there. So let's go ahead and just graph that horizontal line. Okay, that's easy enough. Okay, so there we graph the, then I'll say that's like, you know, y equals 16, or f of x equals 16, whatever you want to say there. G of x equals 16, I guess. That's what they say, g of x. Make it g of x equals 16 there. Okay? And so that was the right-hand side. We've graphed it like it was a function g of x. And we'll graph the left-hand side here, x squared. Okay, so let's recall what x squared looks like. What's the name that we give to the graph of x squared? A parabola, right? Okay, and it's got a vertex. Where's the vertex when you have a graph of just x squared? Okay, yeah, 0, 0. So we're going to plot a point here at 0, 0. Right there. Okay? And then we obviously need some more points here. So how can we get some more points? How can we get some more points for our graph here? We know that it's got the vertex 0, 0, but then what can we do to get more points? How can we graph this? Yeah! Pick some numbers and plug them in. Exactly right. That's funny. So pick a number. What would you like to plug in there? That's funny. 1. Okay. So now we got to be careful looking at our x-axis here. What does our x-axis count by? 2. So when we say 1, we're going to go only halfway, right? Halfway there. So 1, we're going to plug 1 in and we square it, right? So I don't know. I'll make a little table right here. Okay. So I plug in 1, my y value, when I plug it in, since we're talking about x squared here, it's going to be 1 as well. So 1, 1, it's going to be right there. And they're also counting by 2s on the y-axis too, so be careful there. All right, let's try another number. Let's try maybe 2, right? What's 2 squared? 2, 4, yeah. So 2, and then up to 4 right there. All right, let's keep going. What about 3? What would that be? 9, okay. So 3... Again, only go halfway between the 2 and the 4 there. So 3 and then 9, that's going to be halfway between 8 and 10. So right there. And let's do 4. Why not, right? And then 16. Ah, perfect. And then, yes, use symmetry. Exactly right, Greg. So -1, +1. -2, +4. -3, +9. And then -4, +16. And now I can connect those dots. And that makes a very nice parabola. Okay. And the beauty of doing all these points is that we actually get what the points of intersection are, where they're located. Okay? So, identify the x-coordinates of the points where the two graphs intersect. What are the x-coordinates of the points where the two graphs intersect? -4 and 4. Or 4, yeah. Exactly. So those are our two solutions. All right, a single, simple equation here, x squared equals 16, 2 solutions. Both 4, when you square it, gives you 16, and -4, when you square it, gives you 16. So 2 answers there, right? Okay, so let's look at letter B. Letter B has us solving the same equation, but by factoring. Now, when you want to solve a problem like this by factoring, what must it equal? 0. We're going to use that 0 product property, right? That very special property that only only works if it's equal to 0. All right. So to make this 0 here, ooh, man, this is not working here. Let me go. There we go. Okay. So so Connor, what do we need to do to our equation here to make it equal to 0?
Subtract 16 on both sides.
Exactly right. And so we're going to end up with x squared minus and then the 16 right here. Okay. And you can see here they already kind of helped factor it for us. X squared minus 16, that's going to factor to x plus 4, x minus 4. And so then it says apply the 0 product property, so it'll be x plus 4 equals 0 or x minus 4 equals 0. And so then when we solve that little equation, subtract 4 on both sides, you get x equals negative 4, or here we added 4 on both sides, you get x equals 4. So there's another way. But you get the same answers as we did with the graph, which we better get the same answers because it's the same problem, right? Just doing it a different way. So there's those two, right? We talked about factoring yesterday. We talked about graphing, probably last week, I think, sometime, graphing those quadratics. Last thing here, letter C, we're now going to solve by taking the square root. All right? The idea here, right, is that when we solve an equation, when we're solving an equation, what are we really trying to do? We want to get the x by itself, right? But what's with the x here that we need to get rid of? A square. And how do you cancel out a square? You square root both sides. Okay? Now, you've got to be careful, because if you go into your calculator here, this is where we have to, we can use our calculators, they can help us, but your calculator doesn't help as much as you'd like. So first of all, do you guys know how you take a square root in a calculator? Second, and then it's x squared. Down here, you can barely see it. Let's see if I scoot it up. There you go. You can see the little square root symbol there, like that. So I get a nice, square root symbol there. I'm going to put 16 in here. And my calculator gives me just the number 4. It does not tell me plus or minus 4. Right? Which is what we know the answer needs to be. We should get positive 4 and negative 4 here. So plus or minus 4. Okay? So, why does our calculator say only the square root of 16 is just 4? Why does it say only 4 here? But why does it say, why do we know the answer has to be plus or minus 4? Well, here's the difference. Okay? When you are out in the wild doing a math problem, okay, and you see this, maybe you see this, or I don't know, something like this. You do this, and it's simplify, right? And you're oh, I remember how to do this. All right, square root of 16 is 4, plus 5 is 9, and check. That would be your answer. Done. But when you're out in the wild and you see a problem like this, and you square root both sides, the point of an equation is to come up with all of the possible values of x that make the equation true. So, you may say x is 4, and you're right. 4 is a solution, but you're not done, because you still have other solutions you need to be considering. What other number, when you square it, gives you 16? You have to also say negative 4. So you can just simplify that by doing plus or minus 4 there. Okay. So really, anytime you take the square root in an equation setting, right, where there's variables and you're solving for variables, you want to include that plus or minus. Okay. You want to include that plus or minus when you're taking the square root in any equation setting. Now, let me ask you this. Let's say I have this equation. X cubed equals 8. What do we do to solve this little equation here? The cube root. Right? So that's the square root symbol with a little 3 there. Square root symbol with a little 3 there. So that leaves us with just x. Yes, the cube root of 8 is 2. Do I need to put a negative, should I say plus or minus 2 though?
No.
Why not? I did for the square. So, right, the idea is here that the only solution to this equation is positive 2, right? 2 cubed will give me a positive 8. But like Greg was trying to point out there, a negative 2, if I cube it, would give us a negative 8. So no go. Okay? So when do we need to, what's that? Exactly. So anytime we have an even root, So that's square roots, fourth roots, sixth roots, eighth roots, so on, so on, so on, so on, so on. We might later, you know, kind of thing. We'll talk about like all sorts of crazy, you know, exponent stuff and all that. But the idea is for any even-powered root, you do want to have that plus or minus because you're coming from a square, a fourth, a sixth, an eighth, which would then include positive and negative numbers. They would be the same thing. But for the odd-powered roots, you just want to keep the sign the same. Okay, but yeah, you're right, Carlos. We're going to stay mostly in the realm of like squares and cubes for the most part, but we may venture out. We'll see. Who knows? Okay. All right. Let's see here. So we're going to continue on then and take a look at the next here on Explain 1 on page 114, the next page. Okay. So some properties of square roots that we may need to use. Okay, so this is a little introduction here. When solving a quadratic equation of the form ax squared plus c equals 0 by taking square roots, you may need to use the following properties of square roots to simplify the solutions. Okay, in a later lesson, we'll actually like use these properties in a more general form and then prove. So we'll use these like more intensely later, but I want to introduce the ideas to you right now. Okay? And there are two properties, the product property of square roots and then also the quotient property of square roots. Okay? So if you look here, in words, the square root of a product equals the product of the square roots of the factors. Now you might read that and be like, what? Right? The square root of a product equals the product of the square roots of the factors. What that means is, here's the square root of a product, right? The square root of a times b is the same thing as doing the square root of a times the square root of b. So here's another more basic example. Square root of 12. That's the same as the square root of 4 times 3. Now why would we break it up like that? Well, because when we break up the square root of 4 times the square root of 3, what's the square root of 4? It's 2, and so it simplifies it just 2 times the square root of 3. Okay? That's how we simplify square roots, if you guys don't remember from doing that from before. Okay? Quotients, same idea. If you have a square root of a quotient, right, that's division, you just take the square root of the numerator over the square root of the denominator. Okay? And then, so here it is, like square root of 5 ninths is the same thing as square root of 5 over the square root of 9. Again, why do that? Because we can do the square root of 9, it's 3, and so we get root 5 over 3. Notice what's missing here. We have 4 different operations that we use. Addition, subtraction, multiplication, division. We've got multiplication, we've got division, but there's no property for the sum of a square root. So in other words, the square root of a plus b, like this, does not equal, in general, the square root of a plus the square root of b. Okay? That's not a property, right? So that's why I'm showing you they're not equal. You can't break up addition in a square root. Likewise, if I have the square root of a minus the square root of b, also not necessarily the same thing as the square root of a minus the square root of b, like that. Okay? You can't break up addition under a square root. You can't break up subtraction under a square root. You can break up multiplication. You can break up division. It will work, but it does not work with addition subtraction. Okay? So, all right, they want us to rationalize and stuff. So anyway, we'll talk about that here too. So let's take a look here at our next page and see some examples of this in practice. All right, letter A here, for example. It's got it written out for us. We want to solve the quadratic equation by taking square roots. So we're not going to graph this to solve it. We're not going to factor it to solve it. We're going to solve it by using square roots. So you can see here, we add the 16 over, so we get this. Divide both sides by 2. All right, I'm going to write that in here so you can see it more easily. Okay, so we're left with x squared, and 16 divided by 2 is 8. Then we square root both sides, and we're left with plus or minus the square root of 8. Okay, but 8 is the same thing as plus or minus the square root of 4 times 2. Okay, and so why do we do that? Well, because we can break that up to root 4 times root 2, and what's the square root of 4? 2, and so we simplify that. Notice we don't break up that 2 anymore because 2 really can't be broken up anymore. There's no other perfect squares that we can break up that 2. We broke up the 8 into 4 times 2 because 8 had a perfect square in it. It had the 4 times the 2 there. That's why we broke it up that way. Okay. So let's look at letter B here. Letter B has negative 5x squared plus 9 equals 0. And so I'm going to ignore all this stuff right here just because I think it's way too much blank filling in. Okay, so how should we go about solving this little equation here? Let's go to somebody here. Let's go to Jordan. So Jordan, for the first step here, if we're going to solve this, what should we do for our first step? Subtract the 9. Very good. So equals negative 9. And then what? Yeah, exactly right. Divide both sides by negative 5. Okay, those cancel. I'm left with x squared equals. Now, negative 9 divided by negative 5, there's no way to simplify that except the negatives will cancel, right? Because negative divided by negative, so we can make it 9/5. Okay, and then Jordan, now what should we do? Yeah, we're going to square root both sides. So square root the x squared, square root the 9/5. The square root of x squared is just x, and we're going to have plus or minus, positive or negative, and then, the square root of 9/5. All right, well, let's see here. We can break it up to the square root of 9 over the square root of 5, right? And so what's the square root of 9? So that's helpful, right? Plus or minus, it's just 3 over the square root of 5. Okay. Now the book wants us to do one more thing here, and I don't know if I want to worry about that, so we'll hold off and we'll just say that this is our final answer here. Have you guys ever heard of rationalizing the denominator before? Yeah. So rationalizing the denominator, and I'll show you here, but the idea is that, and I'm not sure, and I guess part of the reason why I don't like having to show it to you because I'm not really sure why we have to do it. It's just something that we're told to do, but I don't really have a good reason why right now. There's a square root here in the denominator, okay, and for some reason, I don't know, and so I apologize, because I feel like, I should know that for you guys. I'll look it up, though. A square root of 5, we don't want to leave a square root in the denominator. So, there's a way to get rid of it, and what we're going to do is we're going to take this thing and multiply by 1. Okay, but we're going to multiply by 1 in a sneaky way, or a tricky way. We're going to multiply by root 5 over root 5. Okay, where did I get the root 5 from? Well, it's the fact that I'm trying to make this thing not have a square root anymore. So I'm going to multiply it by another of itself. Okay? Now, I'm allowed to multiply by this because what is this thing valued really as? A 1, right? It's root 5 over root 5, so that's really a 1. Okay, so I'm just going to show you this here. 3 times the square root of 5, it's just going to be 3 square roots of 5. Okay? Well, the square root of 5 times the square root of 5, since both those 5s are underneath the square root, I can multiply them. It becomes 25. Right? The 3 here is outside of the square root, so I can't multiply it with the 5 inside like that. Okay, I'm just going to leave it on the outside. But I do have that 25 in there. And what's the square root of 25? 5. And so that's our final answer there. 3 root 5 over 5. Okay, that's rationalizing. Again, not really sure the point of it, but that is something that we are told to do. Okay? So, yes, with a but there. Like, for example, you might have another number in front here, like a 2 or something like that. Like it might be 3 over 2 root 5, in which case it'll just be 2 times 5, that'll be a 10 down there instead. So essentially it'll work out like that thing will be a 5, yeah. And then you'll root 5. If it was, so if there was square root of 4 in the denominator, that would be easy because it just simplified it 2. No, I know, but that would be nice if it was that, because then we wouldn't have to worry about it. If it was like square root of 7, for example, then you would have, it would be a 7 in the denominator and then root 7 on top. Yeah, so I mean, if you want to help, if that helps you remember it, absolutely. So I would like you guys to go ahead and try numbers 3 and 4 there. Please try 3 and 4. Give those a try, please. 3 and 4, solve them real quick, okay? And please try and simplify the square roots if you can. Try and simplify those square roots if you can. Okay, and I'll come around and help you too. So we're trying number 3 and 4 there, Connor, on page 115. These two right here. Okay, we're trying number 3 and 4 here. 21 shots. find the square root, that's okay. You can just leave it and we'll come around to it too. And ask me. Help too. Okay, Katie, let's go to you for number 3 here, Katie. What should we do? Okay, and then square root both sides. Okay, and so we get x equals. Okay, very good. Perfect. Okay, so right now, Katie's pretty much done. She has x equals plus or minus the square root of 24. We've essentially solved the problem, but we should try and simplify this if we can. And Katie correctly broke down that root 24, right? Katie could have said that square root of 24 is equal to like the square root of 2 times the square root of 12, and she wouldn't be wrong. But she doesn't want to pick 2 or 12. Why not? Yeah, they're not perfect squares. We can't simplify that easily, right? So, we don't want to pick that. She wisely chose to break it down into plus or minus, and you said the square root of 4 times the square root of 6, like that? Yes, very good, because 4 is a perfect square. And so what does it simplify to be, Katie? What's our final answer?
X equals plus or minus 2 square root.
Beautiful, exactly right. Yep, plus or minus 2 times the square root of 6. 6 breaks down further, right? We could say it's root 2 times root 3. But it's not helpful because neither 2 nor 3 are perfect squares. So we're just going to leave the 6 the way it is. It doesn't break down to any other perfect squares, so we're done. That's how we know we can stop. Okay? Very good, Katie. Well done. All right, let's go to Andrew. Andrew for number 4 here. What should be our first step to solve this? Yeah, we're number 4. Okay. Okay. Sorry, I'm slow. There you go. Okay, yes? Then? Not yet. There you go. There you go. Yeah, it'd be 13 over 4, okay?
And then h squared.
Now we square root, right. So x equals, okay, so first of all, plus or minus. Got to put that there now, right? Root 13 over 4, we could leave it that way, but remember we just talked about how the square root of a quotient, you can break up to be the square root of 13 over the square root of 4, like that. Now, why is that helpful? What can we do now that we have it written this way? Right, square root of 13, we don't know what that is, not a perfect square, but what's the square root of 4? 2. So it's the square root of 13 over 2. This does not need to be rationalized, because where's the square root? In the numerator. We only need to rationalize if there's a square root in the denominator. Since the denominator is simplified out, we're done. Thank God for that too, because rationalizing is a lot of extra work. Okay? We're done there. Why not just type in the calculator? That's a great question. So, and did you do that? Oops, sorry. All right. And Jake, did you say something? Why did you have a reason for why you think? Right. Okay. So now, and so I see what you're saying. Right. In like a realistic kind of setting, right? If you're like trying to find measurements or something like that, obviously yes, you would go to this, you would round and be a decimal. In math, right, we're trying to be very precise. That equal sign, while we take it to mean a lot of different things, equals means the same value. When you put in this this square root into your calculator, the square root of 24, okay, and even if you were to put all these decimal points, technically that would still not equal the square root of 24. But like, Mr. Widmeyer, when I type square root of 24, my calculator says that's the value. And yeah, it's the rounded value though, right? This value goes on forever and never repeats itself, right? It's a unique number. It's called an irrational number. So while it looks like, Mr. Wood, I see it repeat right here, 8, 9, 8, 9. Right, but then the next one is 7, and then 9, and then a 4, and then 8, and a 6. So there's no pattern to this. It goes on forever without ever repeating. It's not possible to write it in any other way except for, the square root of 24, right? Some decimals that go on forever, like the fraction 1/3, its fraction, or decimal is 0.3333, it repeats, but this one does not. It's unique. And so any time that we were to round this, it would not be exactly equal, but these are all equal, precisely the same value. So, you're right, Craig. If it was like measurements or something like that, you would totally just round it, for sure. Okay, but that's why we don't do that for right now. And sometimes they'll ask you to round it. For example, questions like this, where we have an application. In this sort of application problem, right, we need to know realistically approximately what it's going to be. So, two commonly used quadratic models for falling objects near Earth's surface are the following. Okay, so here's this one. The distance fallen in feet at time t in seconds is d of t equals 16t squared. So that's like how far you've fallen after, falling for a certain number of seconds. The height in feet at time t in seconds, so here's your height, where and that's called h sub 0, is this object's initial height in feet. Okay, so for both models, time is measured from the instant that the object begins to fall. A negative value of t would represent a time before the object began falling, so negative values of t are excluded, right, from the domains of these functions. This means that for any equation, d of t equals c or h of t equals c, where c is a constant, a negative solution should be rejected. All right, we should throw out negative values because it doesn't make sense in the context. So let's take a look at an example here. Okay. Excuse me. So just as some examples, right? Write and solve an equation to answer the question. Give the exact answer, and if it's irrational, that is, a decimal that goes on forever, a decimal approximation. So like you were saying there, Greg, right? So for example, if you drop a water balloon, how long does it take to fall 4 feet? So we're going to use the model d of t equals 16t squared, right? That's the distance that it's fallen is 16t squared. And we'll just solve the equation d of t equals 4. So we want to know when's the distance equal to 4. So you just set that 16t squared equal to the 4, divide the 16 over so that it becomes 1/4, right, because 4 divided by 16 is 1/4, and then square root both sides. And so the square root of 1/4, believe it or not, is 1/2, right, because the square root of 1 is 1, square root of 4 is 2, so you get plus or minus 1/2. But of course it doesn't make sense to talk about a negative time, right, going back in time from when you dropped the water balloon, so really it's just the positive version, 1/2 second. Okay. Similarly, there's this one here with the rooftop of a 5-story building is 50 feet above the ground, so there's the rooftop. How long does it take the water balloon drop from the rooftop to pass by a 3rd-story window at 24 feet? So in other words, here it is right here. We want the height to be, the final height to be 24 feet. The height initially, right, that's h sub 0 is going to be 50, because you get from a 50-foot tall building, and you want to solve it for equal to 24 there. So I mean, it's going to look like this, basically, right? We're going to have initial height of 50 minus 16t squared equals then that 24. Okay, and then you subtract 50 from both sides, so you get negative 26 here. You then divide both sides by the negative 16 to get that t squared by itself, so it's going to become 26 over 16, which really simplifies to 13 over 8. Okay, and then you square, oh wait, no, I don't want to do that, sorry, I want to leave it 26 and 16, I apologize, and you'll see why here in a second. So then we square root both sides, okay, and then we can simplify that square, we can simplify the square root of 16 nicely, it'll be root 26 over 4. And again, we type that into our calculators then. Okay, so the square root of 26 divided by 4, okay, which is about 1.3, we'll say. What did it say to round to? Nearest tenth of a second. So 1.3 seconds, or root 26 over 4 seconds. Okay, so you may want to keep an eye on those formulas on the previous page there. Okay, I'm not going to have you memorize those, but you will need them for the homework that we're going to be doing later. Okay, we're going to start on them later here in class. So just keep that in mind. Okay, so now we're going to skip those 2 your turns there. Okay, we're going to skip those right now. We're going to go on to page explain 3 here, and we're just about done, I think, is what I wanted to get to what we're going to do here. Yeah. Okay, we're just about done. Okay. So now we're looking at something called imaginary numbers. All right. So you know that the quadratic equation x squared equals 1 has 2 real solutions. And what are those 2 solutions? 1 and negative 1. Negative 1 and 1, when you square them, you 1. Those are the 2 real solutions. The equation x 0, how many does that have? Well, it says 1 real solution. What is the 1 solution of x squared equals 0? 0, right? 0 squared is 0. That's the only number that squares, so it gives you 0. And the equation x squared equals negative 1. X squared equals negative 1 has no real solutions, right? Because there's no number that when you square it can give you a negative value. Right? If I square a positive number, what's the answer going to be? Positive, right? A positive times a positive is a positive. If I square a negative number, what's the answer going to be? Positive, because a negative times a negative is a positive number. So how the heck do you square something and get a negative value? Well, the key here is that x squared equals negative 1 has no real solutions. Okay? And this idea, and this, what we're talking about here, in this meaning of the word real, we don't mean real as in like reality, as in, you know, the things we experience day to day and stuff like that. We mean real as in the way we mathematically define real. There's a real set of numbers, and there's another set of numbers outside the real set of numbers called imaginary numbers. Okay? And so we create a new type of number is created, necessary here to solve these, and they're called imaginary numbers. Okay, they're not real, they're imaginary. And mathematicians created this set of numbers to allow for solutions to equations like this. Okay, and believe it or not, there are applications to imaginary numbers in real life. I'd have to look them up, but I think it has to do with like graphics processing and like your computer card, or like your computer graphics cards, or your like, you know, any sort of graphics, you know, processing and stuff like that, and other things as well. So they are necessary. They do show up in real life, as a thing. So imaginary numbers are the square roots of negative numbers. These numbers can all be written in the form b times I, where b is a non-zero real number and I called the imaginary unit. So there's where that I comes from. If you guys ever wondered, there's like a little I on your calculator here, down here at the bottom above the decimal point. You can barely see it. Okay, that little lowercase I, that's actually a number, and it represents the square root of negative 1. I is the square root of negative 1. Okay? So here's some examples of imaginary numbers. This, 2i. I is not a variable in this case. I is the number, square root of negative 1. Okay, there's negative 5i. Negative I over 3, or the same thing, negative 1/3 I times the square root of 2. Okay, I root 3 over 2, or root 3 over 2i. Okay, so given that I equals the square root of negative 1, you can conclude that I squared is negative 1. Right? If I equals the square root of negative 1, then if you square both sides, you get I squared is negative 1. This means that the square of any imaginary number is a negative real number. Okay, and when you square an imaginary number, we're going to use the power of a property of exponents. So you'll see that. All right, so let's look at this here. Just as some examples. Okay, so for example here, if we want to find the square, there it is. Find the square of the imaginary number. So if we take 5i and we square it, okay, if you take 5i and you square it, you just square 5 and you square the I. 5 squared, what's that? 25, easy, right? I squared, negative 1. So it's just 25 times negative 1, negative 25. Okay? Here, negative I root 2, we're going to square that. So we already have the I squared there. We're going to make this negative root 2. Okay. What's the square of root 2? What happens when you square the square root of 2? It's just what? 2. Yeah, it's just 2. So we 2 times negative 1, negative 2. Okay, easy. Sorry. Hello? Hi. Can do. Gotcha. Bye. Josh, they want you down in the AP office where you brought your check this morning, I think. They want you down there, okay? To see you real quick. Probably something about the computers and stuff then. All right. So, last thing then. We want to be able to find imaginary solutions of simple quadratic equations. All right? So, here's how we're going to work this here. When we see that we're going to take the square root of a negative number, we're going to make it a positive number and then just put an I in front. Right? So, for example, if we want to take the square root of negative 6, we're going to rewrite that as I times the square root of 6. Okay, because remember, what is I? I is equal to the square root of what? Negative 1. And so it just becomes then I square root of positive 6. Okay, so here's an example with 12, right? We make it negative 12. You square root both sides. So we end up with plus or minus the square root of negative 12, which then we make that as plus or minus I root 12. But then that square root of 12, we can simplify, right? We break it down into 4 and 3. And what's the square root of 4? It's 2. So we end with plus or minus 2i square root of 3 then. Okay? Plus or minus 2i square root of 3. All right. Let me do one here with you guys together here. So let's look at number 11. All right, and I'll get you guys started on your assignment here, finally. All right. So, this guy right here, let's solve this equation for x. Now, if you notice here, the directions say solve the quadratic equation by taking square roots, allow for imaginary solutions. So now we're going to potentially have imaginary answers here. Okay, so let's get this done. Let's go to, I don't know, let's go to Adam. So Adam, to solve this equation here, what are we going to do? How do we start solving this equation for x? What should we do? Yeah. Okay. Sorry, AJ, sorry.
Yeah, -9.
-9 on both sides. I know, now I'm just going to get confusing because I keep changing it up. Okay, then what?
Then you divide by 1.
We could divide by 1/4 or multiply by 4. Let's multiply by 4 because that's a lot easier for me to think about mentally, right? So you get x squared equals negative 36. Okay, and then?
And you
Square root both sides, and of course we wanted to talk about plus or minus. And you were going to say that, sorry, I put words in your mouth. All right. So since it's a square root of negative 36, we're going to have to pull an I, right, and make it just root 36 now. Like that. And then what's the square root of 36?
6.
Yeah, so it's going to be plus or minus 6I. And that's our solution there, okay? That root 36 completely simplified. Let's do the next one since that one was so quick. All right, let's do one more here then. Last one. Last one for sure. All right, let's go to Patrick. Patrick, how about this guy right here, number 12? What should we do to start solving for that x squared there?
Subtract 3.
Subtract 3, you got it. Okay, so we get negative 5x squared equals 7. Then? Divide by negative 5 on both sides, you got it. So you get x squared equals negative 7/5. And then? Square root it, you got it. And so we have x equals plus or minus. Now, since it's negative 7/5 in the square root, what can we write in front of that square root then? To not make it negative anymore, what can we write? Say again? I know, they don't break down any nicer. Well, you see here we had a negative root, we had the square root of negative 36, and then I wrote it as plus or minus I square root of positive 36. So what should I write here? Plus or minus I square root of 7/5. And we can stop here, or if we want to rationalize it, we could rationalize it, but I'm just going to have a stop here, because I don't want us to worry about rationalizing right now. That's too much. Okay? So, your assignment, okay, if you turn the page here, here's what I would like y'all to do. All right? So circle these problems, please. Number 1, which has A, B, and C to it. So if you want to circle the A, the B, and the C there. Okay? So please do number 1, A, B, and C. Okay? We can skip 2. And let's see what else I want to do here. I want you to try numbers 3 and 4. Okay? I want you to try 7 and 8. And for 7 and 8, you're going to want to go back and look at those formulas early. Use formulas on page, and let's see what page they were on there. 115. Okay, to help you with those. Okay. So 1, 3, 4, 7, 8. I want you to try number 9 as well on the next page. Okay. So 1, 3, 4, 7, 8, 9. I want you to try, 14 and 19 as well. Okay? And that's all I will have you do. 14 and 19, please. Okay, so once again, I'll read them out loud here. Sorry. 1, ABC, 3, 4, 7, 8, 9, 14, 19. That was on page 120. Is where it starts. And I'll also have it up on the Google Classroom too.
I never got the Google Classroom.
It's on the board there. If you can see, right underneath Algebra 2, it's HKZ, that's a 0, B3I. Okay, so yeah, so feel free to log in. You can log in right now if you want.